My name is Jeff Stout, and I'm here to give the final presentation for Team 41 Revved Up Boards. During the opportunities exercise, the team came up with several potential product ideas, including an automatic plant watering system, a jet-powered scooter, and the product that the team decided to work with, an electric longboard. Our goal was to create a commuting apparatus geared towards college students traveling approximately 1 to 3 miles to and from campus. After deciding on the longboard, the team worked to create a mission statement, including items like key business goals and the primary and secondary markets. Our primary markets included daily commuters as well as college students commuting to and from campus. Our secondary markets included thrill-seeking adventurists. After creating our mission statement, the team then sent out a survey to potential customers to create our customer needs, as you can see here on the slide. Some of our more important customer needs included controlled descent down a hill or braking, a neutral function so that if the batteries were to die and no power can go to the motor, you could still ride the board like a regular longboard, and variable speed and acceleration for traveling up and down the hills. Some of our more amusing and fun customer needs include a GPS with the ability to track the routes that you take while riding the board, and a built-in entertainment system. From these customer needs, the team then created target specification to help develop concepts. From these target specifications, the team then did a mind mapping exercise where we took all of the portions of the project that we knew we would need and create different options. For example, we had a 1-motor system, a 2-motor system. We also had a motor system or a friction drive system or a hub motor system. With the first motor that's not the hub motor, that would be a belt drive system. From there, we used the gallery method to get feedback from our peers in order to improve our concepts. We then went to a scoring and screening method after we'd come up with these 6 solutions as seen on the screen. That scoring and screening method allowed us to whittle down the number of solutions. And though those methods decided that solution 4 is the best solution, the team decided to continue on with solution 1. Due to ease of manufacturing, time spent to create the prototype, and financial responsibilities. Intellectual property is the ownership of a design or invention, often known as a patent. For the project, the team researched related patents that could be used in an electric skateboard in order to see if any could be applied to the project. The various patents, as seen here on the screen, explored could be applied to the project, however, the team would have to pay to use these designs. For instance, we could use the removable hubs that attach onto the wheels and give the wheels spinners like low-riding cars. Also, we could use the rider detection system, which is similar to that seen in segways, hoverboards, and the one-wheel. Basically, what you do is you lean one way or another on the board, and the board can detect that motion and then turn that into power output towards the motor. The team then performed a failure modes and effect analysis exercise for this concept. Some of the major problems the team thought the product might see were failures in the motor mount, failures in the wiring, failures in the belt, and failure in user input control. For the motor mount, we thought that due to the torque of the engine, it might cause the motor mount to break. For the wiring, we feared that the wires may become disconnected while using. For the belt, we thought that the belt might snap due to wear, rapid acceleration, and temperature over time. And for loss of user input control, we fear that maybe the battery will die in the remote, or you lose the ability to talk to the Arduino, which is controlling the electronic speeder control. After performing the exercise, we see that the greatest problem that we could run into is the belt breaking. But due to the modularity of a belt drive system, it allows for an easy fix of this problem, whereas if we had gone with a hub motor design, if a hub motor breaks, you have to replace the entire motor, not just one component. To help test the life of the motor mount, the team ran finite element analysis, or FEA, on the mount. The team placed fixed geometry on the rails located where the motor mounts to the mount, as well as the hole that connects to the truck. We then picked a ferrite stainless steel, which has a yield strength of about 173 megapascals. We then took a torque of 3.57 Newton meters, which is the max torque that our motor is rated towards, and put it on the back face of the mount, which you can't see here in the picture. This torque causes stress locations, as you can see here. And looking at the scale here on the right side, we see that those max out at about 1.96 megapascals, which is significantly less than the yield strength of 173 megapascals. Here, we can see finite element analysis run on the motor gear. For this, the team placed a fixed geometry on the hole that connects to the motor shaft. The team then placed a force on the 3 teeth, as shown here. That force was 493 newtons, which was calculated by taking the max torque from the motor, 3.57 Newton meters, and dividing that by the radius from the center to the top of the tooth, which is around 7.24 millimeters. We then selected the same ferrite stainless steel as the motor mount, which once again gave us a yield strength of 173 megapascals. Running this FEA gave us a stress concentration seen here, but looking at the scale on the right side, it is less than the yield strength, which means it won't fail. Here, we can see finite element analysis run on the wheel gear. For this, we put fixed geometry on the 4 mounting holes, which mount to the wheel to the gear. This allows for bolts to go through the gear, through the hub of the wheel, and then bolt on the other side. The team then placed a force on the 3 teeth as shown here. That force was 158 newtons, which was the max torque of the motor, 3.57 Newton meters, divided by the radius to the top of the teeth, which is around 22.6 millimeters. We then selected that same stainless steel ferrite material, which once again gives us a yield strength of 173 Newton meters. And running the finite element analysis gives us a stress concentration in these locations. And looking at the scale, it maxes out at less than the yield strength and less than the stresses seen on the smaller gear. This is due to the fact that because it's a smaller gear, it sees more of the torque, because when you divide by a smaller number, the number is bigger. Here, we can see a CAD assembly of the longboard with various aspects, including the wheels, the motor mount, motor and gearing assembly, the trucks, the board itself, and the Arduino containment box. The team then performed a design for assembly exercise that allowed the team to estimate the total time it would take to assemble the product. It was estimated that it would take 427.95 seconds, or around 7 minutes and 8 seconds, to assemble the product. If a worker were to work for $17 an hour, the total cost of the assembly of one unit would be $2.02. Here you can see the team's bill of materials, and though the team spent more than they would have liked, the prototype was still built at a fraction of the cost of the competitors. Boosted Boards, which is the leader in the market right now, their equivalent board costs close to $1,400, whereas our total is only $307.74. Some of our more expensive items do include the board, the trucks, the wheels and bearings, the motor kit, the motor, the Arduino, the battery, and the electronic speed controller. Here in this example, we're assuming that the longboard was built by us. All you need for that is plywood, wood glue, and some way to press the wood together so that the glue can cure. In future revisions of the product, there are many aspects we could change to better the product. We could purchase better batteries to improve range and battery life. We could create our own electronic speed controller using breadboards, transistors, and Arduinos to reduce the cost. We could also CNC mill our parts instead of 3D printing. Here you can see one of our gears that didn't work out as well as we could. We had a failure in the teeth due to support material from the printing process here on campus. Because they are trying to print these gears as quickly as possible, it didn't turn out quite the way we wanted it to. But by machining these parts, we could readily and quickly mass produce these items.